Talk to me about free fall, Anna.
Each time an object is falling, the only force acting on it is gravity.
Okay. The only force acting on it is gravity. I want you to just go back to the beginning with the first thing you said. I want you to say it again.
An object is falling.
Let's stop for a second. I want to start there because this implies something which is not correct, and I want to make sure people understand it. Because I know it's called free fall, and often people will say, well, when an object is falling, and the only force acting on it is the force of gravity. What am I getting at? What do I want to make sure people understand?
It can also go up.
When people think of falling, they think of something going down, right? So an object is in free fall even if it's going up. So I don't even talk about falling when we talk about it. It's simply say the only force acting on the object is the force of gravity. Okay. Therefore, the acceleration in the y direction is equal to, Stephanie? Good. Negative 9.8 meters per second squared. Where is this true, Jessica?
On Earth.
On Earth. So make sure you realize that this is the acceleration of gravity here on planet Earth. If we're on different planets, it's going to be different. We'll talk about that. Don't you worry. But there's something missing in the middle there. I want to make sure we put in. Josh, what should be between those two? I'm sorry. Let's make sure I understood that. What'd you say? Negative G, because class, G is equal to what? Positive 9.8 meters per second squared. Are you sure it's positive, class?
Positive. Yeah, it's positive.
I'm just checking. Because oftentimes people have this idea that G, the constant G, is for some reason negative. It is not. G is defined as positive 9.8 meters per second squared. The acceleration due to gravity here on planet Earth in the y direction is actually equal to negative G. Now, I do understand that I've written 9.8 meters per second squared, but unfortunately, I'm going to write that so many thousands of times that we're simply going to, at this point, assume that it has 3 sig figs so that I don't have to write the 0 every time. Unfortunately, I don't think I would do that again if I were to start teaching over, but I have enough inertia with all of my materials that it would be hard to change at this point. There's a lot of inertia there. Chapter 2. Section 2.7 has to do with integrals. We are not going to do that yet. We will come back and talk about the stuff in section 7 of chapter 2 later in the class. Let us now go through an example problem. This is problem 62 from chapter 2. So you are going to need your textbook out. Yeah, I think so. It's hard to make sure I call it. I'm trying, I'm looking around, I'm like, I think I'm calling everybody. There's so many. Yes, Beth.
This is in section 3, or chapter 3.
What's in chapter 3?
The page number 62.
Problem 2. I'm sorry, problem 62 from chapter 2.
Page 55.
I don't know the pages. I don't know the pages. Okay. I see. There we go. We got there. All right. Goolsby, can you please read? And Sydney, can you please translate?
A test rocket is fired vertically upward from a well. A catapult gives an initial speed of 80.0 meters per second at ground level.
Stop. Velocity initial equals to 80.0 meters per second. And the x initial, position initial is 0. This is at ground level. Okay.
Its engines then fire and accelerates upward at 4.00 meters per second squared until it reaches an altitude of 1,000 meters.
Stop. Wait, so we have to do two parts here, I guess. So, the first acceleration for the upward portion is equal to 4.00 meters per second squared. And the final position for that period is 1,000 meters.
Okay, I do want to be careful, we're going upward, correct?
Yes.
So I'm going to use y's instead of x's, just to be clear.
Okay.
At that point, its engines fail and the rocket goes into freefall with an acceleration of negative 9.80 meters per second squared.
Stop. So for the second portion, the acceleration is equal to negative 9.8. Okay.
How long is the rocket in motion above the ground?
Okay, so for part A, we want to find the time spent for the first part.
Actually, let's be careful. What does it say, Goolsby? What are we trying to find?
How long is the rocket in motion above the ground?
So the total time.
This is going to be the total time. We'll get to what that means in a little bit. That's the total time.
B, what is the maximum altitude?
So it would be the position when velocity is at its max.
Let's stop for a minute. There's a lot of pieces to this. So let's back up for a minute and let's draw a picture so we can figure out exactly what's going on. So Goolsby, read for me again and I'll try to draw a little picture here.
From the beginning?
Yep.
A test rocket is fired vertically upward from a well. A catapult gives an initial speed of 80.0 meters per second at ground level. Its engines then
Hold on.
fire.
I don't know if I've ever tried to draw a rocket before. I don't know. I'm kind of impressed myself. But I'm sorry, go ahead.
Its engines then fire and it accelerates upward at 4.00 meters per second squared until it reaches an altitude of 1,000 meters.
Okay, so right here, we are at 1,000 meters. And this is what we're going to call part one. I'm going to write it like this, part one. So initially, we're going to need to call this V1 initial because we're going to have to separate parts 1 and part 2 here. So this is V1 initial, which happens right here. And for part 1, we go up 1,000 meters. And we have an acceleration for part 1. So we should really call this Y1 initial and Y1 final. In fact, I'm going to actually call this the change in Y for part 1 is 1,000 meters because in the long run it decreases. Bye, Mike. Good luck. It decreases the number of variables. I think in the long run for right now, that's a good move. Okay, cool.
Okay. How long is the rocket in motion above the ground? Oh wait, I skipped that part. At that point, its engines fail and the rocket goes into free fall with an acceleration of negative 9.8 meters per second.
Okay, so what do I draw at this point after the rockets have cut off? Bob.
It continues up a little bit.
It's going to continue to go up until it reaches the very top, and then it's going to come back down. So it goes up, and it's going to come back down, and we do need the total time, so we're going to have to draw it all the way until it comes back to here. So let's see. We have velocity 1 initial, which is right here, and we'll call this right here part 2. And part 2 goes all the way from there to there. This whole encompasses that whole piece. I think we're doing pretty well. So delta T total, notice that is going to encompass both parts. So that would be equal to delta T1 plus delta T2. Goolsby, keep going.
How long is the rocket in motion above the ground? B, what is the maximum altitude?
Okay, so what is that? Young.
So it's the primary time.
Okay, so notice that that's like partway through part 2, right? So this is the very top, and our height maximum, which is what we're trying to find, I would illustrate right here. It goes all the way up to there and all the way back down to here. And you mentioned something important about that.
That's when the velocity is going to be 0.
Remember at the very top, that is the point at which the rocket is going to stop briefly before it comes back down, where the the velocity changes direction from a positive to a negative. Goolsby, is that all we're looking for?
And there's a C. What is this velocity just before it collides with the Earth? You will need to consider the motion while the engine is operating separate from the free fall motion.
So, Sydney, what's the last thing we're looking for?
Velocity to final.
Velocity to final equals question mark. General strategy. How do you want to approach this? Quick one. Okay. First thing to identify is that we have acceleration equals a number, so we can use UAM for both. Good. So really, it's just a question of using the UAM equations. John. Which is? Okay. Good luck. Okay, but we're missing subscripts. What subscripts should we put on here? Should we?
They're all one.
Okay, we're going to talk about part one because we have, Yeah, unfortunately, we don't know V1 final, we don't know delta T1, so we cannot use that one. Josh, again.
Use this change in height equals velocity initial 1 times the change in time for part 1 plus 1/2 times the acceleration 1 times the change in time for part 1.
And this is the change of y for part one. So we have enough here. We know the initial velocity was 80. Oh, we know. We can figure out delta t. Okay, good. Okay, we have the change in time, which is 1,000. The displacement in the y direction, which is 1,000. Change in time, 1 we can find plus 1/2 times the acceleration, 1 which is 4 times delta t1, which is, this is great. I love this. So now what? Headlet? We could go and use a different one. If you were going to try to use the, hold up, give me 30 seconds here. If you're going to try to use the quadratic formula, realize you need to actually write out the quadratic formula. You can't just plug it into your calculator. That's called calculator magic, and this is true for the test. You need to be able to show that work clearly. We could do it a different way. Just another 10 seconds. So I'm not going to finish this problem. You can finish this at your leisure. This just starts to remind you of how all this stuff works.